Good morning and welcome. We're delighted that you're all here. I'm Michael Ernst.
Werner Dietl.
I'm going to be talking to you about how to prevent errors before they happen, that is, to prevent errors at compile time instead of letting them happen at runtime. So the motivation for this is that your code is terrible. My code is terrible too, and so is everyone else's. Here is a security appliance that is running, and it's a little bit hard to see here, but here's its output, null pointer exception. So here's a case where a null pointer exception actually leads to an undiscovered security vulnerability. The cost of software failures is very high, $300 billion a year at least, and $300 billion for one particular bug. It can happen fast too. The Knight Capital Group lost $440 million in 30 minutes due to an automated trading error. They don't exist anymore. And there have been high-profile aerospace disasters that cost $500 million or more dollars. Those are the cheap ones. Those are the ones that don't matter. There have been many documented deaths due directly to software failures in radiation therapy machines for cancer patients. Probably the number is much higher. Deaths from bugs in missile guidance systems, in radar software. A blackout caused by a software bug caused at least 11 excess deaths. And software is causing over 25% of medical device recalls. That number is actually much higher today. So fixing bugs matters. Today we're going to talk about a way to verify your code, to prove that it doesn't have certain types of errors. We'll talk about a tool called the Checker Framework. It's open source and freely available. We'll talk about how to use it, and we'll talk about how you can extend it if you want to extend it. So please interrupt for questions anytime during the talk. So we love type checking because type checking prevents you from putting hello world into an int, which is great. But type checking doesn't prevent enough errors. In fact, both of these statements on the bottom pass the type checker, but crash at runtime. Do people know why this first error crashes at runtime? There might not be a console. This will work every time on your dev machine. But then as soon as you deploy it onto something that's headless, then it will fail. In fact, you'll get a null pointer exception right here. What about the second one? Yeah, the collections.empty list gives you an empty collection that's immutable, and so you get an unsupported operation exception, which the compiler should have told you about, but it didn't. Those are the good cases. There are worse errors. Here's an example of a silent error. Suppose we create a new date, and we put into a map, mapping from that date to the string now. Now we round it to the minute, and what happens when we do mymap.get of date? It can't find it anymore. The map is corrupted. So it's going to return null. Essentially, it says, that date isn't here. Here's another silent error. So people see the problem here. It's SQL injection. You shouldn't be taking untrusted user input and just using it as a SQL command. So this leads to a SQL injection attack. And there are a lot of other types of errors. Errors in initialization, in data formatting, in equality tests, and so on. So let's take a look at that last one, SQL injection attacks. So the goal is we don't want to execute user input as a SQL command. And here is some code you might imagine writing that is bad code. It creates a SQL query, and it's looking for this user. So it says select star from user, where user ID equals S, and you put that in single quotes. So the problem is, what if you have a user with an unusual name? Their name is quote or quote X quote equals quote X. Well, now when we concatenate it, the SQL query is where user ID equals empty string or X equals X. That's always true. Now they have access to your entire database, maybe to read it all, maybe to corrupt it or to delete it. So there's a way to prevent these errors, and that's just sanitize the user data before you use it. So here's an example of some vulnerable code. I've made it a little bit more abstract. Where's the bug in this code? Where's the defect? Okay, so maybe the defect is on this line where user input was passed directly to the operation. Is there any other place the bug might be? Well, maybe the bug is up here where we called execute query. You can't figure out where a defect is. So maybe execute query is wrong, maybe user input's wrong. But you can't figure out where an input is, where a defect is, without knowing the specification. And if you find that there's a bug in your program and then you just start making changes randomly, you'll never arrive at a correct program. You'll just get more and more confused. So one specification is that the parameter has to be untainted. The parameter should be trusted. In this case, we can determine exactly where the defect is. Where is it? So it's user input. We should never have passed this untrusted, this tainted value into the operation. On the other hand, maybe the programmer intended the parameter to be allowed to be tainted. In that case, the error is right here. There should have been validation done inside the op operation. Once you write a specification, you can find errors, and you can know with confidence where they are. So I want to do a demo of preventing a SQL injection attack.
In this demo, we'll go through one particular type checker and use it on a real-world piece of software.
Great. So is that large enough for people? Should I increase the font a little bit more? Increase it? More? Okay, great. And if you can't see, move on up. There are seats in the front. So here is a piece of code called personal blog, and we found it on the internet, so it's probably pretty good code. It lets you write a blog and then let people post queries and let people interact. And it has a routine called execute query. And we have annotated that as untainted because it expects to get an untainted value. And then there are a bunch of routines like get post by category that takes a category and it lets you find all the posts that are about kittens or some other important topic for your blog. So what I'm going to do is run the tainting checker on this code to see if there are any SQL injection attacks. And it's complaining. So you can see the bottom here. It says on this line, it found a tainted string, but it required an untainted string. That's because execute query is being given something that's the concatenation of stuff that includes an untrusted value. So it turns out that if you look at the design, they really intended get post by category to take an untainted string. So let's update the specification. That was just a little bit of documentation they forgot to write. So we wrote it for them. Now there's another problem here in a routine call, and again, it's saying you're using a variable called rec category, and it's being passed to get post by category. That's the routine we just saw. So let's look at the definition of request category. It's right here. And what do we do? Well, we do request.getParameter. That's something that's under the user's control. It's the category the user provided. And we make sure that it's not null, because you don't want to have a null pointer exception. But this is untrusted user code. So what the code really should have had was validation. And validate is a routine that will throw an exception if there's a problem with the code. Okay, so now if I run our checker for SQL injection attacks again, then it gives a clean bill of health. It passes correctly. So we found a missing piece of documentation. We found a bug in the code. And even more importantly, now we know there's no more missing documentation about tainted values, and there's no more bugs in the code about tainted values. We have a guarantee, a proof of those properties. Does that make sense? Questions? Okay, good. So what about validate? So does validate definitely do what it's supposed to do? So here's how validate works. And our system doesn't know about some random validation routine you've built. So there's actually a warning suppression right here, because if you run the checker, it will say, hey, you've done a bunch of loops and tests of characters, and I don't understand that. It's not built in. So the proof is with respect to the places you wrote a suppress warning. And everywhere you wrote a suppress warning, you're saying, I swear I have validated this code in some way. I've run a different checker, or I've done code review, or I've done exhaustive testing of it, or something like that. So every type system issues false positive warnings. And in Java, you can get around those with a cast. We use suppress warnings. And it's an indication of exactly what your proof is about. Great question. Other questions? Yes? Good. So what's the default here? So in the demo that I've shown you here, the default is tainted, and you have to write untainted. You can flip the default depending on, if this is a package where most of the strings have some other property. Okay, great. What? Let me see if my slides now work. Yeah.
Okay. Now you've seen a demo of how to use these type systems on real-world code. So what is the verification approach that we're proposing to you? Pluggable type checking. All of you are familiar with type checking because that's what Java provides to you, and we want to make it stronger. We want to provide additional guarantees that you can get during compilation. So the approach for verification is that you design your type system. You say, this property is important to me. I want to prevent tainting problems. I want to prevent null pointer exceptions. All of these different properties we can express as a type system. Then you annotate your code. You provide specifications in these critical places by adding annotations, by providing the specification in your source code. And then through your build system, through your IDE, you run an annotation processor that enforces these properties. And you pick and choose on which parts of your code you run the checker. To illustrate this a little bit more, here's the normal loop for type checking. We have a source code, we have the standard language compiler, and until the compiler is happy, we get errors. We need to fix up our code. Sometimes there are false positives where we need to add casts to make the Java compiler happy. In the end, we have our executable, but we are not quite sure about the runtime behavior of our executable. We can still get runtime exceptions. Optional type checking adds a similar loop. So for the programmer, it's very familiar. You either get a normal Java error, or you get an error from one of these pluggable type systems. And the programmer does the same thing. Hopefully, it provides useful information to fix a bug, but sometimes you need to suppress warnings that are false positives. So there are things that you cannot express in the type system, and you suppress these warnings. The nice thing is that you always get the executable. So that once the Java compiler is happy, you get the executable, you can start testing, user testing, whatever you want to do with it, but only once the pluggable type checker is happy, you actually get guarantees about the behavior. The other nice thing about optional type checking is that you pick and choose what properties you're interested in. It's not fixed that all of you now have 20 different type systems that you need to enforce and annotate your code. You pick, this is a property I care about, and this is what I annotate my code with. So that's the nice thing about making an optional type system. You pick and choose what properties you're interested in. Any questions about this? Yeah?
Why not build it into the language instead of making it optional?
So the question is, why not build it into the language instead of making it optional? So the problem is that not everyone cares about tainting. Not everyone cares about regular expression well-formedness. So there are dozens of different properties, and it would overburden all programmers if you had to worry about all properties at all times. So putting it into Java for some properties might come up in the future, but not in general. So you want to be able to pick and choose what are the properties you care about. And you can create your own. So we call it the checker framework because it's a framework to write your own properties. So even if Java at some point has 10 additional properties that the compiler enforces, there are always business domain specific properties that you want to enforce. Yeah?
And then there's no enforcement at the executable level, right? So you have to have trust boundaries that your, I guess, public interfaces.
Mm-hmm. Great question. So what about enforcement on the executable level? So we are a compiler plugin, so we only enforce the property. I think there's a slide in a few minutes. So we only enforce properties on the source code that we compile. So at runtime, we don't modify the behavior of the JVM. We don't enforce anything about code that we didn't type check. We only give you guarantees for the code that you checked. There was another question? No. So as a second demo, null pointer exceptions. How many of you have run into a null pointer exception at some point in their life? Good, everyone. It's just the biggest problem in any object-oriented language. Tony Hoare called it his billion-dollar mistake because it's one huge design problem in most programming languages that we have null pointers. So we want to present you a simple type system that helps you prevent null pointer exceptions at runtime. What we need to do for this is have a distinction between references that can be null at runtime and references for which we have a guarantee that they are never null at runtime. So we call those nullable and non-null. So and we have the same design problem as we had for the tainting system. Let's look at this very simple operation. We take some input data and we want to convert it into a string. Within it, we invoke a method on this input data, and then some other code invokes the operation with a null argument. Where's the problem in the code? We have exactly the same problem as before. Without the specification, we cannot say. We need to say, did this operation, did method up allow nullable parameters, or did it require that the parameter is non-null? So is it at the trust boundary where you still have to check for null, or is it some internal code that definitely already had to be non-null? So there are two possible specifications. Either we say this argument has to be non-null, then the implementation is correct, but the invocation of the method is an error. Or otherwise, if we mark the parameter as nullable, the invocation of the method is okay, but the implementation has a mistake. You shouldn't directly dereference that argument. Okay, and now Mike shows a demo of this.
Okay, great. Let's go back to code. So here's code from our tool, from the checker framework itself. And it's a type checker, so it has a case for every different type of expression in the Java language. So this is the code that's handling new array. Whenever you create a new array, it's going to type check that and make sure that everything is okay. So what's the code do? Well, first it says, where am I right now? And then it says, what's the enclosing method? What method is this in? Because you might have set different defaults, or there might be some method, some behavior of that method. And then you say, okay, given that I know the method and I know where this is, tell me what the annotations are on it. What's its type? So we wrote this. We were very happy with it. We released it, and it crashed. We screwed up. I mean, we should have had a checker when we were writing this thing. Do people see what the problem is? It's actually a null pointer exception. Okay, well, let's run the type checker, and maybe that'll help us out. So here I'm running the nullness checker on this code. And what it says is, hey, if we look down here, it says, I found a nullable element, and I expected a non-null element. So in other words, it says, get annotations from element is expecting a non-null value, but method is a null value. And we're like, method is a null value? Why is method null here? So it turns out you can have a new array construction outside a method. Where can it be outside a method? It could be in a static initializer block. It could be in a field declaration, the initializer of a field declaration. So we messed that up. So the solution is we should have said, if the method's null, we're going to return this special thing that says there's no annotation there. So now, if we rerun the nullness checker on our code, then it's going to validate that there's no possible null pointer exception anywhere in this code. Okay, so we found a bug there. Let me show you a bug that, so that was pretty relevant to us. Let me show you a bug that might be more relevant to you. Here's a JUnit test. I presume many people here have used JUnit, and here's what it's asking. It's asking, is the null reference equal to the 4-character string null? Yes? No? No. These two things are different. Awesome. Let's run this test. And so it's saying we expect an assertion error. So let's run this test. I'm using JUnit 4.3, and let's see what happens. Whoa. We got a crash. In fact, we got a null pointer exception within the code of JUnit 4.3 itself. Huh. So here is the code for JUnit 4.3. Let's run the nullness checker on JUnit and see what it tells us. So it found 5 problems. Here's one problem, is equals, right? It says there's, if we look down here at this error, it says dereference of possibly null reference. The reference is named expected. So it turns out that this is really supposed to be non-null. If you look at all the places it's always called with a non-null value. So that one's not a huge deal. Here's one that's a little bit more serious. So here is the assert equals method. And it's asserting 2 arrays are equal to one another. So what does it do? It iterates. So O1 is an element from the first array, and O2 is an element from the second array. And what it does is it says, OK, if they're each themselves arrays, we're going to make a recursive call. But that is a terribly wrong thing to do. The reason is I can't call O1.getClass if O1 might itself be null, and we didn't check for that. So the fix is all this code here that I've commented out. So if they're both equal, then continue. Otherwise, if one of them is null, then you fail. Otherwise, if the other is null, you fail. Otherwise, we can ask what their class is and see whether it's an array and stuff like that. So there are more problems here. And this is the one that we actually crashed on. This is the format routine. And the format routine is taking an expected value and an actual value. And it's going to print out a bunch of information about them, because that's a helpful thing to do. So one of the things that it's going to do is going to print out the class of each one. Because sometimes, this has certainly happened to me, you have 2 objects that format exactly the same, but they actually have a different class. So it prints out the class as well as the value. But the value might be null. And then if you try to print out its class, you get a crash. In fact, you get exactly the crash we saw before. So what I need to do here is change that to this code, where we say, if it's null, print null. Otherwise, print its class, which is a helpful thing to do. So let's recompile JUnit. And now let's go back to our test case and run our test case. And now our test case passes. It does exactly what we expected it to do, and JUnit isn't crashing in the middle of your tests. So here we saw, finding special cases in our code. We found failure to check for null values, just randomly calling routines on them. So this, again, helps to improve the quality of the code, and now we know there are no more null pointer exceptions in any of those projects that we've checked. All right? Make sense? Any questions? Okay. Are you up now? Okay. So what are type systems good for? Well, we found a bunch of bugs. I think that's awesome. But fundamentally, I am not motivated by finding bugs. I think it's much more interesting to prevent the bugs from existing in the first place. And that's what we've really done here. We verified, we guaranteed the absence of bugs. Not all possible bugs, specific bugs, right? Just null pointer exceptions or just SQL injection attacks. You choose what's the most important for your project. What's the thing that keeps you up at night? And you verify that for the core parts of your system. Another thing we did was we improved documentation, right? You should write English documentation like this should not be null or this is expected to be tainted, but if that documentation is concise and brief and in the code and machine checked, you know it's correct. You know that you can trust it. And that helps maintainability in code structure. Also, sometimes it can show that there's a bad design if it's difficult to type check. Another thing that this can do is it can help other analysis tools. Other analysis tools can depend on these properties. You could imagine a runtime system that elided checks that have been proved not to be necessary. We don't have a system like that, but that's been done for other languages. Now, there's no free lunch. For every positive, there's going to be some kind of negative, maybe big, maybe small. And here are two possible negatives. One is that you have to write types, right? This is a verification tool. It takes specifications and it proves those specifications are correct and that your code is bug-free. But that means you have to write the specification. You have to write the types. So it's sort of like transitioning from Java 1.4 to Java 1.5 when you added generics. That improved the documentation of your code and it improved its structure and maintainability. Similar kind of thing. You're going to have to write the extra types. We found that I'll talk a little later about what the burden is. There's another possible problem, which is that false positives are possible, right? This is a conservative tool. It will tell you every possible problem with your code, but sometimes your code is so tricky that it can't be sure the code is right. And then it's going to say, whoa, I can't prove this code is right, and it's going to provide you with an error message. In that case, if your code's so tricky it can't figure it out, maybe you should clean up your code. Maybe you should simplify the code. Or maybe you can just suppress the warnings. And we saw the warnings being suppressed in the first example with the SQL validation. OK? Great. So the checker framework is a tool that does this for you. The checker framework is a tool for writing type checkers, for writing more powerful type checkers. And it plugs into OpenJDK or Oracle JDK. You run it using the standard command line argument minus processor, and you provide an argument that says which type system you care about today. And then Java-C issues error messages in its exact standard format, the same way any error message is produced. So that means it integrates well with other tools. So we have instructions in the manual about how to integrate with Ant and Maven and Gradle, and also how to integrate this into Eclipse and IntelliJ and NetBeans. So there are a lot of tools null pointer exceptions, we're not the first person to notice this is a problem. And there are a lot of tools out there that try to help you find null pointer exceptions. So about 10 years ago, we did a little case study where we looked at 4 tools, the checker framework and findbugs and JLint and PMD. And we ran it on this little 4,000-line program that you can think of it as kind of a paragraph grep with a few extra bells and whistles. And so here, can I have the pointer? The checker framework found 9 errors. And the cool thing about that is that it missed 0. We know that's all there is. There's no free lunch. It issued 13 warnings. Right? So 4 of those are false positives that had to be suppressed. And the programmer had to write 35 annotations. And after that, you get the guarantee. So, find bugs in JLint and PMD, the cool thing about them is they just run on your code. You don't have to do any work to get them to run on your code. The less cool thing is that they missed every single error. They didn't find a thing. Because this program had been tested. It was being used by people. These were subtler issues. Could come up. These are real crashes at runtime. It had to be an unusual situation. And they also issued false warnings. In some cases, none. In some cases, quite a few. Okay, so that was a while ago. What about newer tools? So just this past year, we did a comparison with so Eclipse and IntelliJ have built in new, have built in nullness checking. And so here's what their results are. So Eclipse found no errors. In other words, it missed all 9, and it issued 8 false positive warnings. Again, Eclipse and IntelliJ, you don't have to write anything. In IntelliJ, if you don't write anything, it missed everything and issued only 1 false positive warning, so I guess that's better. But you can also write annotations yourself. And IntelliJ is neat because it has an automated tool that will add annotations for you. So we used that tool. We added the annotations automatically, and it added 925 annotations. They weren't quite right. We had to change 8 of them. I think there were 5 that were wrong and 3 that were missing, or maybe the opposite. I don't remember anymore. And at that point, it found 3 of the problems. So it found 3 of your errors. It still missed 6 of them and still issued that false positive warning. So these tools are awesome because they have really slick IDE integration, and so it's easy to run them. But they're not as powerful. They're not doing as deep an analysis. So you should figure out what's right for you. Do you want something that has great integration? Maybe you want to do that at first. But if you really want to guarantee, then you need to use a more powerful system. So you can download our tool and use it. The manual tells you how to do that. But there's also a web form where you can just type some code and play around with it. So what sorts of things, we've shown you null pointer exceptions and SQL injections. What sorts of things can you write with this? The checker framework ships with more than a dozen type systems, and people have written dozens more. External people have written dozens more that they're interested in. So one example is null dereferences. We found over 200 errors in things like Google Collections and Java-C. Another is equality tests. Should you be using equals equals or dot equals? And we found over 200 problems. And that's an optimization people often care about called interning. We found over 200 problems in Apache projects like Xerxes and Lucene. Another is locking. Are you acquiring the right locks in the right places? And we found over 500 errors in projects like Bitcoin J and Derby and Guava. Another is fake enumerations. Oftentimes people will use a set of integers instead of an enum. We found problems in swing and jabref where the wrong values were being used. Strings are a really common source of problems because, you shouldn't be manipulating strings. But if you are, they usually are expected to be in some particular format or hold some particular value. So we have a checker that makes sure that your regular expression syntax is correct. You have the right number of parentheses. You don't, they're all balanced. You don't try to acquire a capturing group that's more than the number of parentheses that were there. And we found over 50 errors in Apache projects, only writing 200 annotations in the entire project to improve the documentation. Another example is printf format strings. You could put %d when the thing could really be an object. And we found 104 errors in a million lines of code and only had to write 107 annotations to find all of those errors. Another example is method signatures. It turns out that Java defines 6 different representations for a method, 6 different string representations for a method signature. It's insanity. And it turns out that the implementation of OpenJDK got it wrong. And we found problems in other tools like ASM as well. We wrote a checker just for ourselves. compiler messages are often have a sort of internationalization kind of feel, and we found that we had misspelled those literal strings in the checker framework in 8 different places. And we also have an internationalization checker that works in very much the same way. Another really important domain is security. So we built, we showed you SQL injection already. We've also looked at command injection vulnerabilities. We found 5 missing validations in Hadoop, where a user could have executed an arbitrary command line string, an arbitrary string as a command line. And then we looked at Android apps, and we detected malware in a bunch of Android apps where private information was flowing to a place that was public. So these are a few examples. There are more documented in the manual, more you can download from their own authors. You can also write your own. If this isn't something that, if you care about something that's not one of these, oftentimes that can be expressed as a type system as well. Hello? Okay, so how hard are these things to use? I've alluded to this a little bit, but this is a really important question. So I think type checking is a really compelling choice for formal verification. First of all, because Java programmers are already bought into it. They're used to writing types. They understand how the type checker works. And this is really just type checking. Once you understand the type system, every rule is exactly the same rule that you learned when you first learned Java. Another neat thing about type checking is it's modular. That means it analyzes one procedure at a time, one method at a time. So there's no long waits, there's no whole program analysis. Also, you can just analyze part of a program if you don't want to analyze the whole program, as long as you have trust boundaries between the places you're checking and the places you're not. Another concern is, okay, is this going to clutter up my code and litter it really badly? You do have to add types, but it's not too many. So for nullness, that's the most verbose type system. We're finding people have to write about 1 annotation every 75 lines. That's many fewer than the number of angle brackets you have to write for Java generics. For interned, as I mentioned, we wrote 124 annotations to find 11 bugs. That was in 200,000 lines of code. For format strings, we wrote 107 annotations and 3 million lines of code to write 104 bugs. Most parts of your code are not dealing with format strings. You only have to annotate the parts that are, but then you get a guarantee for the whole program, which is really neat. As I mentioned, you can annotate just part of the program. And if you're writing new code, you can design in such a way that your design is a clean design. You have to write very, very few annotations. Retrofitting an old design, it teaches you the things you should have been thinking when you designed that old code, and sometimes it's a little bit more difficult. All of these are for retrofitting annotations onto code after the fact. So they're sort of the worst case in that sense. There are not a lot of false positives. There are false positives, but not very many. We ran an experiment where I made students in a class, first-year CS students, I split them randomly. I made half of them use this, and half of them I let use it for the last quarter of the class. And I can never run that experiment again because it found bugs, because all the students who weren't using it had bugs that they got points taken off. And they all said they would have preferred to do the extra work from the beginning to have more correct code. It's also practical. This is used every day on hundreds of projects at Google, on many projects at Amazon, especially for security and compliance. It's used throughout Uber in multiple applications. And people are using it on Wall Street and lots of places that I can't tell you, and other places that I don't know, because it's open source. Give a switch.
Great. Now let's come back to the question about what these checkers guarantee. If you give me 1 second. Okay, so we heard about these type systems. What guarantees do we get out of them? So what we want is that the program satisfies the type property that we care about. So we don't care about every possible bug, every possible specification of behavior. We pick a property, and we want to guarantee that that property holds. We want no bugs of that particular kind, and we also want that the annotations are consistent. If you specify something as non-null, we want the guarantee that the code actually enforces that property and ensures that property. So you cannot cheat your way around the type system simply by specifying type annotations. Before I quickly already started talking about the caveats, this is only for code that you actually type check. So if you have native methods, or if you don't compile all of your source code, you don't get guarantees for that source code. We handle reflection in a very nice and powerful way. So for some of these more dynamic features, we have a sound solution. And we provide many different ways for you to pick and choose what parts of the source code you want to enforce a property on. And as we've seen in the demo, we sometimes need to suppress warnings. We don't want to encode HTML validation. We don't want to encode SQL validation in the type system. So the method that performs the tainting check is a trusted method. So we simply say, this method enforces that the string is not tainted, and we suppress that warning. So we manually, or in some different formal way, verify that this actually is checking for tainting, and then the type checker guarantees that the source code consistently calls that method. So, and even if you just perform type checking on parts of your source code, that might be very useful for you. If it's the trickiest part of your source code and you find real bugs in that part, you are happy. The second caveat is that the checker itself or the checker framework might contain problems. To prevent this, with our academic hat on, if it switches, we formalize these type systems. So we actually perform rigorous formalizations of the type systems and actually want to verify that the properties are enforced at runtime. So this is a part of my PhD thesis, and I like it to show it to people because otherwise nobody reads PhD theses. So our overall goal is that we want to move the power of type systems, make it stronger, and make it more practical. So we want you to think about what are the properties that you're interested in. What features can the type system provide for you to use these ideas in industry? And our goal is to make pluggable type system one strong, expressive, powerful verification approach. Do we have any questions so far? It's a good break. Yeah?
I don't think it's something you said that when you're writing new code, you may not need as much annotation. Why wouldn't you need as much?
Okay, so the question is, I claimed that annotating existing code is harder than annotating new code. And the reason is that you should have been thinking when you wrote your code about making a clear distinction between all the strings that are possibly tainted and the strings that are not. Or you should have been thinking about handling null in a clean way. But you could always just throw in an if-null test somewhere. Or you could always do other things to sort of work around this. So one of the things I like about a type system is sort of pushes you toward a cleaner and nicer design. And that design is going to have a better distinction between the types, and it's likely to also be easier to understand. Another way to think about it is, way back in time, you had some choices to make. You had no way of knowing which you should choose. But then, by the time you get all your code done, you may realize, and you start to run some other tool. It says, this is not a very good design. Then it's harder to move all the way to the better design than it would have been at the beginning if you'd known it from the very beginning. That's a great question. Other questions?
So we don't call it trust inference. Okay, so the question was about trust inference. If you have method bodies and you have an annotation on a field, do you also need to annotate your method bodies?
Is that the question? I think so. Basically, I've assigned something that was guaranteed to be not null. Is that lost if I don't also annotate the local field as not null? Or, like a new var keyword, you guys infer, oh, well, this is final, so clearly it's not null because the thing it's assigned to is guaranteed to be not null.
So the framework provides several features that help you minimize the annotation effort. Our goal is that within the method body, you hardly need any annotations. So in your example with a local variable, we would propagate the annotation from the field or from the method invocation to the type of the local variable. A little bit later in the presentation, we talk about flow-sensitive type refinement. So we have support that if you have a null check in your code, if you check if x not equal to null, in the then block, we refine the type of x without you having to introduce a new variable. So that's a great question. Annotation effort is one of our biggest concerns. How do we minimize it? And within method bodies, we use this flow-sensitive type refinement to pretty much deduce the information from method signatures from field annotations. Any other questions? Then let me show you another example. How many of you have ever wrote in a regular expression and the regular expression was wrong? Yes, a very common problem. Regular expressions are very tricky to get right, and they're in strings. So the Java type system doesn't help you. For the type system, it's just an opaque string. So here I want to present you a simple type system that helps you express this string has to be a regular expression. So in the first example, that's a valid regular expression, but the one parentheses, not a valid regular expression. Very simple distinction. But we want to go even further. We want to be able to specify the number of capturing groups in that string. So regular expression allow you to separate your string into different capturing groups, and different string have different numbers of capturing groups. So here are two valid examples, quite hard to see, and then an invalid example, because why is that invalid? So here's a simple code that uses regular expressions. It's a main method where we get the regular expression and the content from the command line. We compile the regular expression, match it against some content, and then we want to output the first capturing group. Do you see problems with this kind of code? Well, let's just run it. So here I have this example. So we have two command line arguments, the regular expression, and the content that we want to match against. So here, okay, the first one is some regular expression, and we match against the string. Boom, we get a pattern syntax exception. The Java compiler happily compiles this code because it's just strings. But then at runtime, it tries to compile that regular expression and sees, okay, I opened the parentheses but didn't close it. So let's fix it. I didn't even need capturing groups, so why did I have parentheses? But now I get problem like this, index out of bounds exception. So why do I get an index out of bounds exception? Because my source code acts, if the pattern matched, it simply directly accessed that first capturing group. So you even have to check how many capturing groups are actually in that regular expression, and only then are you guaranteed to be able to access it. So now let's run a very simple type checker on this example. So we simply call our Java compiler version with the processor that enforces regular expressions consistency. And we get two errors out of it. The first error is that in this pattern.compile, we found a string, but we actually require a regex string. Pattern.compile is that method that threw the pattern syntax exception. So the input to that should always be a valid, well-formed regular expression. So that might seem straightforward. You just have a string, you check that that string is well-formed. But then here, you have the matcher, and you access the first capturing group out of the matcher, and the type system tracked that information. The type system tracked that the regular expression string that you compiled didn't have any capturing groups. So here it complains that we have an invalid group parameter 1, only 0 groups are guaranteed to exist for this matcher. So we get the type system understands flow sensitively how many capturing groups are in your code. So if we modify that example, what can we do to prevent this? We need to enforce that the right number of capturing groups is contained. So let's look here. We have the 2 exceptions. Now what we need to do is, if there is not a single if there's not at least one capturing group in the regular expression, we want to exit. So we call system.exit. Well, let me skip actually typing that. But the point is that you have this flow-sensitive type refinement, so even without adding a single annotation to your code, because the type system sees if the annotation, if the regular expression doesn't contain at least one annotation, you exit the program. So after that, you know that this string contains a regular expression with at least one capturing group. You didn't need to add any annotation yourself. It's just from understanding the behavior of this isRegex method, you get the guarantee about your program. Yes?
When you write the regular expression in your code and check it with a type checker, is there an error or?
So if you add a regular expression annotation in your code, so let's say.
No annotation, but you, in the first line where you are,
Yeah?
and you type the regular expression itself. And then you run the type checker. Is there checking
So,
capturing group or not?
so like this?
Yeah.
Okay, so let's see what the compiler says. So now it sees that, okay, this string literal was a valid regular expression, but we didn't find any capturing groups in that string. So now let's add a capturing group. So that should be a capturing group in the string. Let's run it again. No more errors. So the the type checker actually analyzes that string literal and sees how many capturing groups are there. And then again, we didn't need to add any type annotation. So alluding to your question from earlier. It sees this is the string literal that gets assigned to this local variable, and therefore I know a more specific type than what the programmer specified. So if we have code like regex equals just A again, so something that doesn't have any capturing groups, the type system will refine the type again. And so now we only know that it's a regular expression. So that's an example of this flow-sensitive type refinement, that for each line of the code, we try to determine the most specific type. Any other questions? Okay. So some of you might be wondering about the syntax that we've been using. So since Java 5, there are declaration annotations. So in your source code, you can use that @ symbol to provide meta information about your program. Java 5 annotations were only legal on declarations in your program. So on a field, on a method declaration, on a variable declaration, but that's not good enough for a type system. So we couldn't specify that null references in all possible locations. We couldn't specify a null list of English strings or a non-empty array of English strings. So the programming language, this annotation mechanism, was not flexible enough. So Java 8 added a mechanism called type use annotations that refined where annotations can be used in your software. So now you can write at null and data, my data, or more interesting, a null list of English strings, or a non-empty array of English strings. So you always write a type use annotation to the left of the type that you're annotating. So, and this is possible in every possible location of a type use. So not just on declarations, types in declarations, but also in casts, in implements clauses. So all possible types in your program can now be annotated and that's what we need for the type systems. The Java compiler itself does the same things it always does with annotations. It passes them, makes the basic well-formedness checks, and then, depending on visibility, retention, stores them in the class file. And you see them in JavaDoc if they're documented, all these things. Then you depend on external tools like the checker framework to add semantics to these annotations. The basic Java compiler just performs the basic well-formedness checks. So one frequent question is external libraries. How do we convince the compiler what the behavior of some third-party library is? So we need some annotations. We need some information about that external library. Otherwise, we need to make conservative assumptions. Depending on your type system, this might be okay, or it might be too conservative. So we provide two mechanisms to specify the annotations of an external library. One is a text-based format where you can just say, for Java-lang object, this is a property for equals. The other one is a binary format where you specify, you take complete Java source code, compile that into an annotated jar file, and then provide that jar file on the boot class path to the compilation. So two very flexible mechanisms to specify annotations for external libraries. And together with the checker framework for nullness and some of the other type systems, we provide annotations. So we have the whole JDK, or the parts of the JDK that we tested, annotated for these type systems. And we have some external libraries like Guava, where we provide annotations. All of these are deployed on Maven Central, so you can just depend on our annotated version of Guava to get these annotations. So what are a few other of the facilities that the checker framework provides? Our goal is to make it as easy as possible for you to write a new type system. So all the basic mechanisms that you would expect from a type system are there. We traverse the abstract syntax tree, perform the basic subtyping checks between the right-hand side and the left-hand side of an assignment, the arguments to a method invocation, and the method itself. So all these basic mechanisms are provided by the framework. And the only thing that you need to provide are specifications for your particular property. We handle generics in a nice and general way, and also have qualifier polymorphism, where you can have methods that are normal Java methods, but are polymorphic in the type qualifier. Defaulting is a big topic. We provide declaration annotations on methods, classes, and packages that allow you to specify what the default for your type system is. So you can pick and choose what behavior you want. Maybe the default behavior for a particular type system is not good in one of your legacy code. So who has a guess what the default for the nullness type system is? So we had this type system where we have nullable and non-null. What qualifier should be the default for this system? Non-null, very good. So the default in Java is actually nullable, because all references can be nullable. But there has been a study that if you pick non-null as the default, the overall annotation effort for your code is much lower. So by default, the nullness checker assumes that your references are to real objects, and you only have to specify nullable when you need it. That highlights the dangerous code in your software. But maybe for some legacy software, you want these standard Java defaults. So you then just specify for that package, okay, here, use nullable as the default. So you can flip the default very nicely. We have pre- and post conditions that allow you to specify the behavior of methods. So in the regular expression example, you saw this isRegex method. That method actually has a post condition specifying that if it returns true, the first argument is a regular expression. And then the data flow framework takes care of propagating that information into the two branches. And warning suppression, we have a very flexible mechanism how you can configure where to suppress warnings. So next, let's think about what type systems would be interesting for you.
Can you turn on this mic? No, they can't turn on this mic. Okay.
So great. We showed you a lot of properties, And sometimes people who aren't very familiar with type systems are surprised that all these can be expressed as a type system. I think that's mostly because most people haven't been exposed to very good type systems. I mean, and in particular, one thing that we've mentioned is I think every type system should give every expression a different type on every line of the program. If it's after an assignment or after a check, this is information you can know, and you can know it soundly and correctly. So what I want to do now is help develop a little bit of intuition about what properties can be expressible as a type system. So we're going to do a little brainstorming, and you're going to mention problems you have or that you've seen in your code, and we're going to talk about whether that is expressible as a type system or whether it's not expressible as a type system, because some things aren't. Like, make sure that there's a Java dot comment on every line of, on every method. That's not a type system property. That's not a property about values. So when you think about a type system, you should think about there's some runtime problem that you want to prevent. It might be an exception, but it also might just be a corrupted map or a SQL injection, something like that. Next, think, can you divide all the data in the world into two parts? And what are the properties of those two different types of data? And finally, what are the operations that are legal for that data, and what are the operations that are illegal for that data? So anything that has a dependency on values, the values that are allowed at runtime, or anything that has a dependence on provenance, where data came from, those are great type system properties. But type systems are not good for things about program structure, not good for things about timing, and so forth. Let me show you a couple of examples. So one example is the nullness checker. So what is the runtime exception we're trying to prevent when we think about running the nullness checker? Yes, null pointer exceptions. Very good. So what are the two types? Thank you. I'm glad someone has seen that. What are the two types of data that we ended up dividing the world into? Yeah, things are either null or non-null. And then non-null references are always non-null. And so what operations do we want to permit or prohibit? What operations do we want to prohibit? Do we want the compiler to stop you from even compiling that code? Exactly. You should only dereference non-null references. And also in synchronized blocks, and there are about 9 places you shouldn't use non-null in a Java program. The checker knows them all. Here's another example, the regular expression checker. What were the runtime exceptions we were trying to prevent? There were 2 of them. Yeah, that the format should be correct and that the group should be correct. So we don't want to have a pattern syntax exception, and we don't want to have an index out of bounds exception due to regular expressions. So how do we divide all the data into parts? These are strings in this case. How do we divide strings into groups? Yeah, there are strings that we know are regular expressions, and there are strings that could be anything. I don't know. But we actually divided it into an infinite number of groups, because we divided it into regular expressions that have at least 0 groups, and regular expressions that have at least 1 group, and regular expressions that have at least 2 caption groups. And then also there's the strings that who knows what's in those things, but we shouldn't be using as regular expressions. And then what operations were we going to allow and disallow? And it's based on, this is always going to be based on these properties of data. What are the operations we want to permit or prohibit? So pattern.compile should only be called on things that are a legal regular expression. And then getting groups should only be permitted if there's that many capturing groups. So now we'd like to brainstorm a little bit and think about what runtime exceptions, what's another runtime exception you might care about? Okay. So that's a great example. So it's index out of bounds exception, right? Is this your computer? Oh, you have to type. No, you have to type here. So index out of bounds exception, excellent. So how am I going to divide all the data in the world into 2 groups, or maybe more? Another way to think about this is, when you look at an array, dereference, how do you know whether that one's okay, or whether you should be sweating a little bit? Okay, so you need to know, for every array, you need to know something about its size. That's one possibility. So since you're doing a sub 0, that thing had better have at least one element. That's one thing to do. What's another thing, another way you might know that a sub I is legal?
I must be positive or non-negative.
Yes, I has to be non-negative. And sometimes you know the exact size of an array. This one's length 5. But other times you just need to know that I is less than the length of whatever A happens to be. So there are array properties and there are index properties. And sometimes to determine A sub I is legal, you need to think about both of those properties. In other cases, just one of them is enough. Essentially, you need to know the index is non-negative and is less than the length of the array. Okay, so then, I just gave away the last part. So the index should be positive and it should be less than or equal to the length of the array. This is a great example. And this is a problem that most people have not tried to address using a type system because they think type systems aren't strong enough for this. But the checker framework ships with a type system for exactly this. So if you want to eliminate the null pointer exceptions in some part of your code, try running it on that. Great example. Is there some other runtime exception that you don't enjoy having?
Can I give you a harder one?
Sure.
I want to be able to annotate a lambda to be side effect free.
Ah, okay, good. So the goal is to prevent undesired side effects. So essentially this is immutability, right? It's not the same as immutability. Purity.
Pure functional.
Yeah.
Because you do have the documented annotations, if you will, in the Java Stream API. It says this lambda that you pass should be side effect free, which I think most people don't even know what that means. But.
Right, so this is a great point. So purity is a really important property that you'd like to have of methods and of lambdas too, either way. And they've already written in the documentation, but they wrote it in English. Right? How should documentation be written? Documentation should be written in a formal way as annotations which are more concise, unambiguous, and machine checkable. So here it's what are the properties we care about? They're essentially, we've mixed together, well, if you're thinking about data, you might want to prove that some data is immutable regardless. But if you're thinking about a method, you want to say that the method doesn't have any side effects. The method is pure. So that's, in some sense, a method property. And then what operations should be legal or illegal? So when are we allowed to call a pure method? Or alternatively, what operations are allowed to happen inside the body of a pure method in order for the type checker not to reject that annotation on that method? Can someone suggest rules we might want?
Pure methods should only call pure methods.
Yes, so that's one. Pure methods should only call pure methods. So right, you can't have modifications in pure methods. So the checker framework ships with a pure annotation and a side effect free annotation. And so you can go ahead and use that. I'm not sure how well it works for lambdas. Does it work for lambdas?
So the problem with lambdas is that there are no declaration annotations on the lambda itself. So I think that's one problem. But we should be able to infer it. One problem with the current purity annotations is that they're trusted. So one of our research projects is a type system that enforces purity. At the moment, these are trusted specifications, so you can say this is a pure method, and we need that in our flow-sensitive type refinement. So if you invoke an arbitrary method, you need to lose information in flow-sensitive type refinement. If you invoke a pure method, you can keep more information around. So that's the current use. And for lambdas, we need to work on the type inference for these purities.
So there's a command line argument to turn on checking of pure methods, but it's pretty strict. Like if you create a local variable, then you're not allowed to call impure methods even on that local variable. Like in toString, you often create a string buffer, and then you modify the string buffer. But toString is a pure method. So our system says, whoa, look at that. You're calling a side-effecting method inside a pure one. That's not allowed, even though it should be allowed for that particular case. So that's a weakness of the current implementation. That's why the checking is disabled by default. It's trusted. So that's a great example. Okay, other issues or other examples people can think of? And then that one wasn't even a runtime exception, right? It was just a thing that went wrong in your program. Yeah.
Classes don't create any new IO types like threads or database connections in structures. Only the dependency injectors class.
Okay.
Sort of related to that last one. Kind of like the same thing on class level.
Right. So the property here is that the constructor should not make any calls should not construct new IO. Okay, so good. I'm going to actually generalize that a little bit and say the problem is determinism. So what we oftentimes when you run a program, you'd like that program to run deterministically. Like I like to be able to compare logs between two executions, and if so, what's a great non-deterministic class that people use all the time? Hashmap. It's terrible. Because if you run your program twice and you iterate over it, you could get output in a completely different order. This is just a bugaboo. So we have research projects right now that are building and that are experimentally running a determinism checker that says, okay, every object, so in this case, the properties are every value is either deterministic, which means it has the same value on every execution, or it's order non-deterministic, which means it's a collection that has the same values, but they might be in an arbitrary order, or it's non-deterministic, which means it could have arbitrarily different values on every execution. And then on an order non-deterministic collection, you can call sort, but you can't call for each. On a deterministic object, you can do anything you want. On a non-deterministic value, you can't print it. And maybe there are other places you can't use it. So this actually doesn't answer your question at all, right? Because I've just described a general framework that we've implemented, and it's in a branch if you want to be brave, that is about non-deterministic values in general, but it doesn't, I guess if you...
That's actually my question. That
Yeah.
is what I wanted, so
Okay.
that's the right answer. That's
Okay.
the right answer, it's the wrong answer.
Right. So that's a great example. And again, one people usually don't think of as being amenable to a type system. People usually write much more heavyweight analyses to try to deal with it, if they do it all. Great. Other brainstorming ideas? How are we for time?
We have 45 minutes. So I think we're good.
Reading from application properties, make sure that it's correct type and parsed.
Okay, so that's a great example. So the example is, let me rephrase it and you tell me if I've got it right or not. So sometimes I have a properties file. Maybe it's for internationalization, maybe it's for dependency injection, maybe it's for something else. And it has some text file, and it's going to be read, but I might have references to that. I might read references to that from somewhere else, or I might have references to it in my program. And I want to make sure that all of those are actually consistent. So is that what you're saying, or have I misunderstood?
No, more that something is like an integer or a number in your properties file, and you want to make sure that at runtime it will always be working.
I see. So I have a properties file, and so one issue would be, do I get the keys in the property file correct? And we already described how to do that. But you're saying, what about the values in the property file? Maybe that should always be an integer, or maybe that should always be a string. So
that's in some sense saying, is the file format correct? Right? I mean, your code is going to just say, I'm going to read from the foo property, and then I'm going to cast it to an int, or I'm going to call toInt on the string that I read. And that's really, is the file format of the file correct, as opposed to, is there an operation that's allowed to be permitted? We could imagine telling you to be sure to check before calling the toInt, but that doesn't, I don't know, does that feel like that is, I mean, it seems like there's a simpler solution than a type system.
Well, so the problem is, how do you specify what your property file looks like? So at the moment, you don't really have a specification that this particular key has this particular value. So I think there's this disconnect. So for checking whether the key is contained in the property file, that's easy because you just check, is that string in the file? For the types of the values, how do you even specify that? I think that's the problem we would have to think about. How do you specify what the expected type is?
Yes, and also that if you run the program locally, you might get a very different properties file in production, for example, if you don't have any control.
Yeah, so we mentioned this compiler message checker, where we check whether the keys are in the compiler key file. So that property is checked at compile time. Then if at deployment you removed the file or something, you will get the exceptions. So the guarantees are, again, when you type check. So if you have runtime dependencies, so a type checker could go to a database and check a property about the database, see whether usernames are in a file, whatever other property you want to check. But that check happens at compile time. So you have to make sure that the state is consistent between what you checked at compile time and what you have at runtime. So you could imagine having a type system that adds runtime checks, so where you add additional code. At the moment, most of our type systems don't add additional runtime checks. Does that answer your question?
So the type system will tell you when you've... Okay, yeah, this one. Okay, sorry. A type system is great for telling you when your code is wrong or when you've forgotten a check. But it's not as good. So I'm a huge fan of type systems. I think they solve a lot of problems. But it seems like it's not quite the right thing for checking that your file format is correct. But it's an important and interesting problem. Yes? Yeah, so that's a great example. So suppose you have a field, and you annotated the field as non-null. Then whenever you access that field, you're going to get a non-null value, right? Totally wrong. And the reason is during initialization. If you call a method in the middle of the initializer, it could see that field as not yet initialized. Or if that's a field in class A and class B is a subtype of it, the A initializer could finish and then call some method, but that method via dynamic dispatch could have access to the B. So initialization is a huge problem. The problem here is how do we ensure that all the data that you're passing around your program is fully initialized, that nothing escapes from the initializer, or if it escapes, it only goes to places that are safe for it. Okay, so what do we want to say about an object? What are the properties that you might want to say about an object that is expected by a routine or that's just true of a particular expression in your program? Maybe that's too broad an answer, but essentially there are two types of values in the world. There are values that are fully initialized and values that are not initialized. Now, the checker framework actually ships with this kind of check because you can't write a nullness analysis without it. I mean, okay, every other nullness analysis doesn't, but we wanted to get it right. So we're able to say it's initialized up to being A, or up to being B, or it's fully initialized. And then every routine, by default, a routine is only able to accept things that are fully initialized. But you can annotate some routines as saying, I promise that I will never call any dynamically dispatching routines, and then it can take a partially initialized thing as long as it only looks at the local fields instead of calling arbitrary methods. And so when you run our nullness checker, you're really running 3 checkers under the hood. One about nullness, one about initialization, and one about map keys. Because if you do map.get, that can always return null, even if your map only contains non-null values. So we have a type system that tracks for every expression what are all the maps that it's a key for. So we know whether map.get might possibly return null, or it definitely returns something that's in the map. So nullness is actually a pretty complicated example, just because of all the crazy ways that you can use null. Oops. Yeah. Do you want to move on? Or more examples?
Are there other examples?
Other problems. These are all actually great examples. String length. Okay, that's a good one. So the issue is that I might want to ensure that a string has some particular length. Maybe I want to make sure it's exactly 80 characters so it fills up the console. Or maybe it shouldn't be more than that. An example is that Windows command line can only take commands up to, I think, 8195 characters, whereas Unix shells may be able to do larger ones. So this was a bug in Bazel and Blaze, the Google build systems. And so you want to make sure that strings don't get longer than that. So we have a string length checker. So we have a string length checker that's shipped with the checker framework for addressing exactly these sorts of problems. You can think of it as a specialization of the array indexing one that I talked about before, but it's really much simpler because it's just keeping track of strings. So it knows whether a string is of a particular length or whether there's some bound on the length. And more generally, the checker framework has a constant propagation. For every value in your program, it has an estimate. And sometimes the estimate is, I don't know what this is an int. But sometimes the estimate is, this string I know has one of these particular lengths. I know it's either length 10 or 20 or 30. Or I know this particular integer is definitely between 0 and 9. That's a great example too. And all that's pushed through your program in a flow-sensitive way. So you usually don't have to write very many of those at all. If you have to write them, it's all as specifications on method signatures, where you're documenting what the expectations are or what the results are. Great example.
Cool. Okay. Great examples. And so some of these are already implemented in the checker frameworks, but for some of the others, maybe you want to experiment in how to do this yourself. So it's called the checker framework. So it's a framework that allows you to write your own type systems. So here's a very simple example. We want to ensure that encrypted communication, that communication only sends encrypted strings. So we have a send method that only takes encrypted strings. If you pass an encrypted string as argument, the type checker should be happy. Otherwise, we want a warning. How complicated would you guess is it to write the type system for this? Do you need a PhD? Yeah, so how do you determine that's encrypted? That's again the human verification. So we say the encryption method itself is trusted and the type system takes care of propagating that information. So but writing a type checker for this, for some reason it doesn't finish loading. It's just 3 lines of code. So you only need to specify. No, I go to the demo in a second. So you only need to use a.
The last line is just
the
public interface encrypted.
Yeah, so it's just the specification of the annotation. So let's just go to the source code. So here we had the regular expression example. Here's the encrypted example. So we want to make a distinction between encrypted string and unencrypted string. So we have this public interface encrypted that specifies this should be an encrypted string. We need a few inputs. We write some JavaDoc. And here is a framework functionality where we say this qualifier should be a subtype of this other qualifier. So we build up the qualifier hierarchy that we use for type checking. Then this line is just the Java functionality to tell it that this actually should be a type use annotation. The second qualifier is this possibly encrypted. So it's possibly encrypted because it's the super type. It's either encrypted or unencrypted, and we don't know which one it is. So here we say this is the subtype of nothing. That's the top in our type hierarchy. And we use another functionality of the framework. It's the default qualifier in hierarchy. So we say for this type system, assume that it's possibly encrypted. We don't know for sure, so assume the worst. And then it's again at interface. So that's all we need for this type system. We just need to specify declaratively the two annotations, what the relationship is between the annotations, and what the defaults are. So here's an example application that uses this annotation. We have this encrypt method that takes an arbitrary string and returns an encrypted string, and it does that by going through each character, encrypting each character. So it's a terrible encryption algorithm, but that's what we have for this demo. And then there's a second method, encrypt character, takes an arbitrary character and performs some super secret computation, how to get the encrypted character. And then we have the send over internet method that takes an encrypted string, does whatever network communication it does. And here we have a method send password. Here we just get the secure password and we invoke send over internet. So this is clearly something that we want to prevent. So let's see what this type check, how we invoke this type checker. So Java check is our alias for the checker framework compiler. We have a type checker called the subtyping checker that is fully declarative. So you just parameterize it by the annotations that you want to support, and you do this with the second command line flag. So you invoke this subtyping checker processor and provide the encrypted and possibly encrypted annotations that you just saw. And that's it. You have this type checker. If we run this on this encryption demo, we should get 2 errors. We get one for this encoding of the character, where we have some numeric computation, and we don't know whether that numeric computation actually gives us an encrypted character. And the second one is the send over internet method, where we directly passed the unencrypted password to send over internet. So how do we fix these 2 errors? For the sending the password over the internet, we actually need to encrypt it first. So here it's just adding this encrypt. We need to encrypt the password before we're able to send it over the network. The first error is trickier. We don't want to encode how to verify encryption in the type system. So here we say this is a trusted method. Here we just say add suppress warnings. Let's see whether this does it. And voila, the 2 errors are gone. So we made sure that the internet communication only works over these encrypted strings, and we highlighted that, okay, on this line of code, you have to trust me. I verified that this is a perfectly safe offset encryption, and this is the kind of encryption that I want. So if I change my mind about what kind of encryption I want, I just look for suppress warnings encrypted, and I see all the places where I trust my encryption algorithm. Any questions about this demo? Yeah?
The annotation to suppress the warnings, the string that you're putting there, is it like a case-insensitive version of the annotation?
Exactly, that's what we do. So just to make it easy. No, you saw everything that's there. So it's really just those 2 annotations, and for the subtyping checker, we use the annotations as suppression keys.
I use Eclipse. Eclipse sometimes it's very picky about giving you a warning about that suppression.
Yes, that's an unfortunate feature that you just have to turn off that warning, because they check for the fixed set of strings that come with their version of the Java compiler, which is also inconsistent with OpenJDK Java compiler. So if you use this suppress warnings, by default you get a warning from Eclipse. So if that bothers you, there is no suppress warnings on the suppress warnings. So you really you have to turn that off in Eclipse. Any other questions? Yeah?
It seems like there's a lot of properties that are sort of like X or not X. Is there a generic way to express that in checker, or do you need to create an X and not X type?
So the generic thing is the subtyping checker. That takes care of taking an arbitrary lattice and then performing these subtyping checks. So you don't want two qualifiers that we give you called top and bottom, because that wouldn't be very good documentation for your software. You want to specialize it and say, okay, I want an encrypted and possibly unencrypted annotation. And then this subtyping checker does all the logic for you. So the hope is that you define the semantics or the good names for these qualifiers, and the framework does everything else for you. But we, at some point, had top and bottom annotations, but it's just not a good idea to use them, because it's just generic bland names that you shouldn't write in your software. Does that answer your question?
Yeah, so like top and bottom, and then you can provide like a value
Okay.
as the sort of like top possibly unencrypted, bottom encrypted.
Yeah. So you could imagine building a system like that. It's probably not a good idea to do that. But if you prefer a system like that, the framework should provide everything that you need for it.
It's better to just suck it up and write the 7 lines of code so you have 2 well-named annotations.
Okay. Okay. Yes.
A related question. All of these seem to be essentially kind of yes or no binary, kind of 2 value space.
Yes.
What does it extend to, like, what if I have 10 types of things, or 100 or 10 million?
Yeah, perfect question. So here is how you more generally define a type system. So what I showed you was this subtyping checker, which takes the declarations of the qualifiers and the subtyping relationships between them. We have declarative mechanisms for many things, so you can define what are the defaults for which literal to use which qualifier, but at some point the declarative way runs out of steam, and then you have to write your own type system. But writing your own type system is also not that hard. So you just saw me declare the qualifier hierarchy for this very simple type system. If you have something more complicated, yeah. Do you want to switch?
Is that showing? Yeah. Okay, great. Is this where we were? Okay.
Great.
Okay, sorry for the... Okay, so we saw how to define the qualifier hierarchy, and that gives the basic information to the type system. So you tell the type system, these are the annotations I care about, and this is the basic hierarchy. The second step are type introduction rules. For which literals do you want to use which annotation? What defaults do you want in your system? Then any specific type rules, the subtyping checker only enforces the usual subtyping relationships. The right-hand side of an assignment is a subtype of the left-hand side. Arguments to a method are subtypes of the method parameters. If you have anything more specific, you have to override some functionality. And finally, flow-sensitive refinement. So defining the qualifier hierarchy is the simple declarative mechanism to say this qualifier is a subtype of this other qualifier. Type introduction rules, we have many declarative mechanisms to say for this particular tree, this annotation is implicit. So this string of this particular format always have this annotation. If this is not powerful enough for you, like in the regular expression checker, you actually have to compile the string literals to determine how many capturing groups you have. You implement it yourself in the annotated type factory. Finally, defining a type system. For example, for the nullness type system, we have to enforce in all the 12 places where we have a nullness check that the reference is actually non-null. And here, one example for a synchronized block, we need to make sure that the argument for synchronized is non-null. So you override a visit synchronized method and then make sure that the type has the annotation not null. Or if it doesn't have, we raise an error. So it allows you to override the mechanisms of the tree visitor to exactly say what the type rules are for your system if the subtyping check is not enough. And finally, flow-sensitive type refinement is this idea that after certain statements, you have additional information about your program. The simplest example is if you have a null check, you know that the dereference is safe. So you can provide some of this information with pre- and post-condition annotations in your code or on these methods, or otherwise you implement it in the data flow framework. What is the data flow framework? It's a very nice and powerful framework that allows you to take Java source code and produce a data flow graph out of it. So you have a nice control flow graph, and we provide all the mechanisms for you to provide an analysis over that control flow graph. This framework is so nice that even other tools started building on it, including Google's ErrorProne and Uber's Nullaway, that wanted analyses over Java source code. And if you're interested in that, you can specialize the data flow framework by providing what information do you want to track for variables, what do the particular operations do, and how do you propagate intermediate results through your source code. Everything else, all the fixed point operations that you need, are performed by the data flow framework. Okay, that's about the framework and features of the framework. Next, Mike.
Okay, so great. I also wanted to follow up on two other things. One is people said, well, why don't you write a type system to verify the encryption routine? It turns out that that's a super hard problem. There are millions of dollars being spent every year on that problem right now. No one knows how to do it, and certainly not in a type system, which is a simple and effective and fast verification methodology. The other is, can we handle more than 2 types? Yeah. We have type systems that have a dozen, and we have type systems that have infinitely many, like the regular expression. It has infinitely many. Okay, so now I want to talk about some practicalities, because at this point, I expect all of you can barely keep your hands off your laptops because you want to start using this on your code right now. So one tip is that you should really start out by type checking just part of your code. Think about the part of your code that's most important to you, or most in need of work, or has the most problems, and really just start locally. You're going to get most of the benefit from type checking the most important part of your code. Another is only type check the properties that matter to you. So some people will say, wow, this is the best thing ever. I'm going to use 20 type systems all at once. This is insanity. You don't need all those. There's something that really matters to your business case. And again, start with that. Later, maybe you can add another one. Another is, so do you really want to be using type qualifiers? If you can use subclasses, then the Java type checker will do all the work for you without you having to use an external tool or write any annotations. Now, oftentimes you can't do that. You can't do that whenever you have to deal with a legacy system. You can't do that whenever you're using built-in types like string, which is final, or int. So there are a lot of places where type qualifiers are also much richer because we have qualifier polymorphism as well as regular Java generics polymorphism. So this system is more powerful, but if what you can do fits in the Java type system, use the Java type system. That's the right way to go. The fourth point here is write the specification first and really think of it as a specification. Say, I'm going to document my code and I'm going to figure out what my design is, and now it's going to be documented in a formal way. If you just start running the system and trying to fix problems locally, you're not going to end up with a comprehensible design, and you're unlikely to end up with a system that works at all. A fifth is it's really tempting to just suppress warnings. If there's something you don't understand, just shut the system up. Well, if you just shut the system up, the system isn't doing any work for you. So try to understand what the problem is, try to fix the bug or poor design in your system if possible. Think of warning suppressions as, I swear and would put my life on the line that this really is a true property. And finally, I hate to have to say this, but you should never use raw types like list. You should always use generics. If you're still using raw types, you're so far behind the curve on sort of type checking that don't try to use this. I want to contrast two different approaches that are both valuable. One is a verification approach, and the other is a bug finding approach. The checker framework is on the left. The checker framework is a verification approach. There are many fine bug finding approaches. The goal of verification is to prove your program is correct, prove that there's no bug of a particular property. The goal of bug finding is to catch the low-hanging fruit, find a few bugs, and don't have to do much effort to do it. So in verification, the user writes specifications. You write the documentation of what your code is supposed to do. Because the only way to ever find a bug is to compare two things. The code against the tests, or the specs against the code. In bug finding, the tool guesses what your specs probably are and then tells you some things that are probably inconsistent with those probable specs. In verification, there are no false negatives. A false negative is when your code is buggy, but the tool says, hey, looks good to me. In bug finding, some number of false negatives are acceptable. False positives are when your code is actually correct, but the system says, whoa, I can't figure out that that's correct. And verification techniques have false positives, and the user has to suppress the warnings. Bug finding tools have false positives, but they use a lot of heuristics to try to eliminate those and make sure that they never even bubble up. They're either far down in the list or they're never even shown to the user. So each of these has a downside. The downside of verification is that there's a user burden. The user has to write the specifications. The user has to understand the type system and fix the problems. The downside of bug finding is that it misses bugs. It doesn't necessarily find everything. So neither one of these is a better approach. Each one has different trade-offs. So you should be using bug finding over your entire code base all the time. You should be using verification on the parts of your code that are really important to you for the properties that you actually care about, that actually matter to you. Because you're an engineer, you're proud of your work, and you want your work to be correct, and your customers probably want that too. All right? So the Checker framework is an open source project. Everything is licensed under either the MIT license or the GNU GPL, just like Java-C is. Here's the GitHub URL. We make a release every month. We have about 14,000 commits over more than 75 authors, and you can submit bug reports and we'll get to them. If you have questions, we'll answer them. There's also an extensive manual and a FAQ and that kind of thing. We're continuing to actively extend this. So we are building new type systems for immutability and determinism. Those are some things that people mentioned here. We have many type systems you can already use, and we're also building some for signed and unsigned numbers and for some other things. Those are all sort of research projects that we think are really interesting problems. Another really interesting issue for us is type inference. So the Checker framework says, if you're willing to write the specs, we'll give you a guarantee those specs are correct. Your code conforms to those specs. But maybe you don't want to write those specs. Or maybe you don't want to write those specs for all the libraries that your code uses. So we're actively working on type inference. We have some prototype type inference you can already use. We already have type inference that's very solid for within method bodies, but I'm talking about a system that takes as input a program and produces an output a program with all the type annotations on the method signatures for you. So you can already play with the prototype tools, and we're continuing to make those more powerful. And another thing we could imagine for the future is including dynamic enforcement as well. Right now, it's a purely compile time tool, produces identical bytecodes, has no runtime overhead, but that also means the suppressed warnings are not checked at runtime. You could imagine trying to combine those, and there are people who are working on that. So if you are able to do time travel, then yesterday you could go watch our talk about how to create a new type system. If you're not blessed with that, then we have one more talk later today, which is at 7:30. It's a BOF, where we'll be giving a lot of the nitty-gritty about how type annotations were added to Java, how to write them and understand them. We'll be talking about what what's holding you back in your company from using verification tools like this. So I think you'll enjoy that. We hope to see some of you there. So the bottom line here is type checking is good, and pluggable type checking lets you customize it and you control it. It makes your code better. We built the checker framework mostly as a way to let us scratch our itch because we like building type systems. But this has found a lot of industry uptake because type systems have these type systems have a lot of features. They're very effective at verifying your code. They're easy to use and they scale to real industrial projects. So the goal here is to prevent bugs at compile time, not to let your customers or hackers discover them later, and generally to improve your code. So go out there and create great code. Thanks for coming. So we have plenty of time for questions, and we'd be happy to answer any more if people have them. Yes?
I don't want to burst the bubble, but we've tried twice now to implement the checker framework. I will say I'm going to give it a third try. So the first time was in maybe 2016. I think there was still, we were running into errors with the checker itself when we crashed. I think that was just early framework. Now the problem is adoption. So the difficulty is, and I'm trying to figure out how to do it properly. Let's say you want to start with a null checker. If you turn it on by default, it's checking, it's assuming everything is not null. So you get 10,000 warnings, which I don't like 10,000 warnings in our code because it might obscure another warning that I really need to pay attention to. So we figured out, okay, well, through the package info, there's a way that you can change the default on a package level. It doesn't seem to work if there's in a class at that level, but then maybe a Java issue. So we struggled through that a little bit, got that to work. But then we started to fight with the fact that we're running Java 11. And so not clear on, especially with external libraries,
Right. So the,
I'm really trying to look at what is the gentlest way, and I understand your perspective is, oh, well, you really should turn these things on. I want to turn them on incrementally with as few numbers of suppress warning lines all over our code, and to adopt it, and as I say, incrementally, so that we
Right. So the question is about the practicalities of adopting it, right? You've got a big existing code base. You don't necessarily want to turn everything on over the entire code base. So we have the checker framework. When you run it in Java-C, it takes command line arguments that can say, ignore this package, or change the default for this package, or only focus on this one package. That's the way I would start. And, you know,
ignore the entire JDK if you
yeah.
want to, okay.
Yeah, absolutely. And there's a command line argument for that. I mean, so if it's a specific question about some specific command line argument, I'd be happy to take that later. So there, essentially, we've had lots of people. So it's not trivial, right? It's a powerful system, but we've had lots of people adopt it successfully. And you know, if you've put issues on the issue tracker, then I'm sure we've addressed them. And if we haven't, please ping us. There was another question here, which was you're going to Java 11. So currently, the checker framework works with JDK 8, and we have a branch that is working with JDK 9, 10, 11, and we have not yet shipped that. But we're hoping to do that in the very near future.
But you can configure it to say, assume nullable for, you know, for example, if you're using the nullable checker, you can say, look, just come on JDK 11, assume nullable for.
Yeah, there's lots of configuration options like saying assume nullable in this package or whatever. Yes, question.
How do you see base used more in the context of code reuse? We use, for example, check style and find bugs. We Sputnik that basically introduces their findings as, you know, a robot's code review,
Yeah.
right? Are you thinking along those lines as well?
Okay, so that's a great question. So oftentimes we like to have an automated code analysis that runs during code review and makes suggestions, says, why, consider this issue. So we run, on many of my personal projects, I just run the checker framework and it's part of the build. So it's actually part of the compiler. I don't need to do it in the review. In terms,
A little more, you know, along
Sure. Yeah. Yeah, so maybe you're not ready for that. The issue with code reviews is that the checker framework, the contract, the promise of the checker framework is, if you're willing to write the specs, I'll tell you all the problems. So if you just start to run it during code reviews and no one's been writing the specifications, it's going to give you a lot of warnings saying, hey, you didn't tell me about the nullness of this routine, or you didn't tell me about the regular expressions in this routine. It really is, should be thought of as part of the language and part of the types, as opposed to this afterthought. The cool thing about bug detectors, again, I said this earlier, is you don't have to do any extra work, they just work. And that's really, a verification tool isn't really a linter. So my recommendation would be start with some specific small part of the system, get that right, and then expand as you improve your design and improve the robustness of your system. So it's a great point, though. Yeah, question?
So let's say I incrementally enable more and more checkers, I fixed the issues in my code base, and finally I've done everything with the checker framework. There's nothing more to flags, it's all done. I'm not nowhere near that. It's not even started. But let's say I get to that point, what's the performance impact on the build that the checker framework can add?
Okay, that's a great question. What's the performance impact on the build? This is the one thing we're not very proud of in the checker framework. So you will, because what have we done? We have a plugin to the Java compiler that re-implements everything the Java compiler does. And that means that, you know, overloading resolution, overriding, all the subtyping checks, and with a richer type system too. So this means that you'll typically see a factor of 2 slowdown on the compile. And for things like the nullness checker, which is actually very sophisticated, we just scratched the surface of it, it can be much larger, you know, even up to an order of magnitude. We don't usually see quite that much, but remember, you only have to run it on the changed files, right? Because it is incremental, and I think that's the saving grace there. But yeah, I won't lie to you. We've had people who say, this is a fantastic tool, but I'm not willing to, you know, increase my compilation times from 5 to 10 seconds. And you know, that's just a decision you'll have to make, and I'm being honest, we haven't focused on that kind of optimization. And because we're doing a lot of stuff, it's hard to completely eliminate the overhead. So it's a great question, a fair question. Yes? No, if your build system knows which Java files to compile, then it's only going to compile those Java files. Yeah. I mean, that's going to do it on the whole file level rather than method by method, which would theoretically be possible, but not possible with our tool. Great. Was there a question over here? No? Yeah, is there another question there? Okay, well, we're around all day, and we have some time right now. Thanks for coming. Thanks for all the great questions, and go make your code better.